To help you understand this worksheet, I'm going to go back to chapter 5. So just put your papers and pencils down for a minute and watch this, and hopefully it will kind of springboard you into helping you with z-tests and t-tests. And really, z-tests and t-tests are what statistics is for. That's why we do statistics, especially with research. Now, some of the chapter 25 stuff we did is also helpful in statistics, but really it's the Z and T, and then other. There are lots of other tests that you're not going to get to. So, in chapter 5, we learned about the normal curve. Okay, so let's say we're playing a dice game, and it doesn't really matter what the rules of the dice game are, but when everybody plays this dice game and we compile all the results, we expect this to happen, whatever it is. It could be a sum, it could be an average, it could be a percentage, it could be just counting up the number of eights. Whatever it is, we expect that to happen. But not everybody's going to get that. We know that if we go out 1 SD on both sides, we will capture 68% of all the people who play the game. And then we could do 2 SDs and we get the 95 rule, 3 SDs, we get the 99.7 rule. Okay? So we can also figure out what's the chance that we land here. How likely is that? Well, the further away we are from the center, the less likely that's going to be. Okay? And once we get to the point where there's only like 5% on that tail, so if this tail is 5%, then that particular point is very unlikely. It just doesn't happen often enough for us to expect it to happen when the person plays. Okay? And if we go out even further and we say that this tail is 1%, then that's almost impossible as far as statistics are concerned. Okay? Now, it still could happen, but we've sort of chosen the 5% and the 1% rule. Okay? Then we moved into other things where we had to calculate SEs, standard errors. Okay? Which had to do with how many draws are you going to make. If you do 100 draws, then your SE is going to make the chance of being further away from the center less. The more times you draw, the more likely you are to be in the middle, right? So we had to convert our SDs into SEs, and then we can do the chapter 5 stuff all over again. Okay? Well, we're finally to a point where we don't know what's going to happen. We're drawing tickets out of a box, and we don't know how many tickets are in the box. We don't know what the percentage of a particular value is, or an average or something. We don't know any of that stuff. So what we do is we make some kind of assumption. Okay? And that assumption is told to us by somebody else. It's claimed by another research group. It's just some number that's given to us, and we assume that it's true. Then we do a sample. Well, how likely is it for our sample to land in the 5% window on one side? It's very unlikely, right? So if we land in the 5% window, or sometimes the 1% window, then we turn around and we tell this person, you're wrong. The number I got by doing my own survey is so far away that I don't think your assumption is correct. Does that kind of make sense? So the whole point is to determine, is this reasonable or is it unreasonable? Well, if we land inside of 5%, we call this unreasonable. If we land somewhere over here where my area is bigger than 5%, or it could be on this side, so let's say that's 16%, is it likely to land inside a 16% tail? Yeah, it happens all the time. and we sort of get to choose how accurate we want to be. So we call this the null hypothesis, and we call the tail the alternative hypothesis. If the tail is 5% or lower, or in some cases 1% or lower, then we reject the null and we accept the alternative. Okay? Let's say that my p-value is 3.4. That means I have a tail that is 3.4%. Does that mean I only have a 3.4% chance of being wrong? Or sorry, being right? No. That just means there is only a 3.4% chance to land in that space if everything was done correctly, which we consider to be extremely unlikely, and so we would reject the null. You can't say I have a 3.5% chance of being correct, because you're either correct or you're not, right? The true value is out there somewhere. We just don't ever know what it is. So you can't say I have a 3.4% chance of being wrong. You have to say there is a 3.4% chance to get a value that far away, and then we would reject the null. Does that kind of help? Now, we do this in two tests, and there are actually lots of tests, but the two we're focusing on now are the t-test and the z-test. And they're basically the same thing, but the t-test is something you do when your draws are small, 100 or less than 100. And if you have to do a t-test, you also have to inflate your SD to make up some of the difference of having a non-normal result. Okay, so number one, it is believed that most teenagers eat an average of 960 pounds of food in 1 year. Where does that come from? Well, to tell you the truth, I just made it up. But somebody claims that. Okay, they did a study, they guessed, they measured their own kids. I don't know. That number we are going to assume to be true. So I can already start drawing my curve. And this is 960. What sort of number is 960? It's an average. Why does that matter? That tells me which SE I'm going to create. I'm going to create the SE average, okay, which is the SD divided by the square root of the draws. Do I have to change that answer into a percentage? No, that's the only difference between an SE average and an SE percentage. An SEP needs to be changed to a percentage, and SE average does not. So we do our own study, and we measure the eating habit of 144 teenagers. So 144 teenagers means we use a z-test, not a t-test. Could I use a t-test? Yes, the t-test will always work. It's just extra effort, and once you get above 100, it doesn't make much of a difference. So we just kind of ignore it. So my D is 144. That sample ate an average of 1,000 pounds of food with the standard deviation of 110 pounds. So here is 1,000 with an SD of 110. Do I use 110 in this case? Yes. Why? I don't have the SD of the 960. Whoever made up that 960 or told it to me didn't give me the SD. If I know the SD of that 960, then I use it. Or if I can create it, I use that. But in this case, there's no way to make it, there's no way to get it, so I have to substitute the SD of the sample. Okay, so now I need to create the SE average. Does everybody follow so far? Okay, so I take 110 and I divide it by, so 100 and, I'll get it. It'll take me a day or two. And I'm going to divide it by the square root of 144, which is 12. and I get 9.16 repeating. Okay. Now what do I do? Find the z-test statistic. So 1,000 minus 960 divided by 9.16 repeating, which is 40 divided by the answer, and I get 4.36. I already know what I'm going to do. Oh, I didn't set up the hypothesis. Back up. What is the null hypothesis? So the true average is equal to 960. Or you could say there is no difference between 960 and 1,000. Or at least that difference can be explained by chance error. Okay? So the alternative says the true average is greater than 960. Why don't I say the true average is 1,000? And that's not my point here. If I wanted to take a sample and to find the true average, I create something called a confidence interval. And I would take the 1,000 and I would add or subtract two SEs, and I would say I'm 95% confident the true average is somewhere in this window. Okay. So I end up with a z-test statistic of 4.36, which means I'm going to reject the null. What's the breaking point for rejecting the null? Well, we need a right tail area of 5% or less, and that 5% mark is 1.64. What is the 1% mark? 2.76. So I already know I'm going to reject the null and accept the alternative hypothesis. But we have to label this in terms of percentages because the world out there doesn't understand what a standard error is. So I need to shade norm. I'm going to shade norm from 4.36 all the way to infinity, and we've decided infinity is the same as 5. So clear my draws. And then I will shade norm from 4.36 to 5. And you're not even going to see it on my graph because my graph only goes out to 4. So you won't even see the area. But even if I was zoomed out more, you wouldn't be able to see it. And I get an area of 6.2 e to the negative 6, which is 0.00000062. How likely is it for the 1,000 to be correct? Extremely unlikely. The percentage in that right tail is 0, essentially. So we reject the null, we accept the alternative hypothesis, and what does that tell us in the context of this story? Do we believe that teenagers eat an average of 960 pounds of food a year? No. Do we know how much they do eat? No. We just don't think it's 960. We think it's some value bigger than 960. You could set up a confidence interval. So you could do 1,000 plus or minus double 9.16. And then we could be 95% confident that the true average is somewhere in that window. But that's not what this problem asked us to do. Okay, does that help? So, new problem, number 2. A casino has been losing money at the coin flipping game. They are starting to wonder if the coin they are using is not fair. In the last 1,000 flips, 520 of them have been tails. Is the casino correct in assuming that the coin is biased? So, what value do we want to put right here? We could do 500. but 50% is easier. Whenever you have a choice between a sum and a percentage, choose percentage. Okay? So 50%, and we ended up with 52%. That doesn't seem very far away, but we did 1,000 flips, which is quite a few. So let's run the numbers. My D is 1,000. What SD am I going to use? The 50 or the 52? The 50. You always use the center as the SD associated with the center when you can. When you can't, then you substitute in the other one. So I'm going to do the SD shortcut, the square root of 0.5 times 0.5, which we already know is 0.5. What do I do with that number? Find the SEP, so I divide it by the square root of 1,000. So 0.5 divided by the square root of 1,000. And I get 1.5%. Whenever you calculate the SEP, you need to convert it into a percentage. Okay, so now I calculate my z-test statistic. Oh, wait, z-test or t-test? Z-test, why? My draws are big. So I do 52 minus 50 divided by 1.5. So that's 2 divided by 1.5. And I get a z-test statistic of 1.33. Oh, I forgot to set up the null again. Okay, so the null hypothesis says what? The coin is not biased. So let's put coin is fair. And then the alternative would be the coin is unfair. More specifically, it lands on tails more often than it should. So we could say tails is greater than 50%. All right. So I get a z-score of 1.33. We know whether we reject or accept now. What would we do? We would accept. How come? 1.33 is smaller than 1.64, and 1.64 creates 5%. But in order to solve this correctly, we need to shade norm. So clear draws, and then I will shade norm from 1.33 to 5. And we end up with a p-value that's quite large. My p-value is 0.091, which is bigger than 5%. So what do we tell the casino? Your coin is fair. You just shade norm. The p-value is just the area when you shade norm. It's the area of the tail, either the right tail or the left tail. 9%. The p-value is 9%, 0.09. So we tell the casino, as far as we can tell, your coin is fair. So why have you been losing money? You've just been a little bit unlucky. Yeah. All right. Next, number 3. The same casino wants to know if a particular dice is biased. In the last 625 rolls, the number 4 has only shown up 13% of the time. Is the dice unfair? Well, how often is the number of 4 supposed to show up? 1/6 of the time, and 1/6 is 16.6 repeating percent. Okay, and we ended up with a 13%. So we want to measure this area, and that area is called the p-value. If the p-value is greater than 5, we accept the null. If the p-value is less than 5, we reject the null. So in this case, the null says that the dice is fair, which means that the 4 shows up 16.6 repeating percent of the time. And some professors get super technical on what your null is going to be. In my opinion, those are the same thing. Okay, so I don't get too caught up on exactly how you write your hypothesis, because the whole point is just to say, is the dice fair or not? So the alternative hypothesis would be that the dice is unfair, meaning that 4 happens less than 16.6% of the time. Okay? Which SE am I going to create? SEP, so I need an SD. They didn't give me an SD, but this is a percentage, so I can use the SD shortcut. 1 minus 0 times the square root of the big times the square root of the small. So in this case, it's just the square root of 16 point, oh, I got to do the decimal, huh? 0.1666 minus 1 minus 0.1666, like that. So that gives me an SD of error. What did I do wrong? Oh, I subtracted it, duh. It's a multiply. Okay. Now I get an SD of 0.372. I'm going to divide that by the square root of 625. The square root of 625 is just 25, so divide by 25. Now I need to change that to a percentage, 1.5%. Okay. Well, how far is it from 16.6 to negative or to 13? Negative 3.6 repeating. So I'm going to take negative 3.6 repeating and divide it by 1.5. Oh, oops. Negative 3.6 divided by 1.49. And I get a z-score of negative 2.46. So to find this area, I'm going to shade norm from negative 5 to negative 2.46. Comma 0, comma 1. And I end up with an area that is 0.6 or 0.7%. So this area here, P, is equal to 0.7%. Do I accept the null or reject the null? I reject the null. Okay, so what do I tell the casino? Your dice is unfair. And in statistical language, we would say that the number 4, the difference between the number of 4s that you get and the number of 4s that you should get is highly significant because we're less than 1%. So we do think that that dice is unfair. Okay, any questions on that? All right, next page. It is believed that Orangeville has a disproportionate amount of males in the city. So a proportional amount of males would be half, 50%. A sample of 18 Orangeville residents has 13 males in it. Ooh, problem. 18 is very small, which means we need to do two things. We need to use the t-table, and we have to create the SD plus. Okay, so first we assume that there are 50% males. So the null says that males are equal to 50% of the population. The alternative says males are what? Greater than or less than? Why greater than? What does our sample suggest? Our sample suggests greater than because it's 13 out of 18. So greater than 50%. Okay. So I need an SD. What is the SD when the percentage is 50%? 0.5. And I'm going to divide that by, or wait. That's the SD. How do I create the SD plus? I need to times 0.5 by the square root of the number of draws divided by the number of draws minus 1. And all that's going to do is make my 0.5 a little bit bigger. So my SD plus is 0.5145. I made it a little bit bigger just to be safe. Okay. So the answer that I got from my survey was 13 out of 18, which is 72%. I need to create a t statistic, which is just like a z statistic, except you use the SD plus. So I need to divide this by the square root of 18. So 0.5145, and I divide that by the square root of 18, and I get 12.13%. This is my SEP. Any questions so far? No? We get that? Okay. So now I need to find the difference. 72 minus 50 is 22. I divide 22 by my SEP. 22 divided by 12.13. And I get a t-score of 1.81. How do I use a t-score? Well, you got to go to the t-table. Which row do we look at? The row is called degrees of freedom. And degrees of freedom is equal to the number of draws minus 1. So we go to row 17. And in row 17, where does 1.18 land? Between 5% and 1.81 lands between 5% and 2.5%. Does everybody see that? Okay. So, do we accept the null or reject the null? We reject the null. Right? So, this area over here is somewhere between 5% and 2.5%. So, do we think there are more males in Orangeville than females? Yes, we do. Even though we only did a sample of 18, we inflated our SD to be a little bit more careful, and we used a t-test, which is like inflating the SD even more. And when we looked at it, we still landed in that 5% window. We reject the null and we say, according to our survey, we believe there are more males in Orangeville than females. Could we be wrong? Yeah, of course. That's the beauty of statistics. You never tell anybody you're sure. You just say, yeah, we don't think so, or we think so. Okay? Number 5, Wikipedia states that the average height of fully grown women in the United States is 64 inches. A sample of 12 women yields an average of 63 inches with a standard deviation of 3. Does that information contradict the Wikipedia parameter? So the source of all knowledge says 64. We run out and we do a survey. We're kind of lazy, so we're only going to survey the girls in this class. There are 12 of you, apparently. Okay, so when we do our survey, we end up with 63, and our SD is 3. So some of you might say, oh, Wikipedia is wrong. We ended up with an answer that's smaller than that. And you said, wait a minute, we expect chance error to happen. The question is this 1 inch difference too big to be explained by chance error, or is it totally explainable by chance error? Well, we need to do a t-test. So the null says that the women average is equal to 64 inches. The alternative says that the women average is less than 64 inches. And all we have to do is find a p-value. If the p-value is less than 5%, we reject the null. If the p-value is bigger than 5%, we accept the null. So I have an SD. I need to turn it into an SD plus. So I take 3 and multiply it by the square root of 12 divided by 11. What is this going to do to my SD? It's just going to make it a little bit bigger. 3.13. Okay. And I need to create a t-score. So, well, I need to do it. I need to divide this by the square root of 12 to get my SE. Oh boy, messed up. All right, so this number here divided by the square root of 12. So my SE is 0.9. Do I need to change that into a percentage? No, because these are averages. Okay, so my t-score is going to be 64 minus 63, and then I divide that by 0.9. So 1 divided by the answer, I get a t-score of 1.11. And it's actually negative, but the t-table only deals with positives, so we're just going to pretend that's positive. What row, oh, sorry, go ahead. 1.11. What row do I look at? Row 11, which is the number of draws minus 1. So I look at row 11. Where does 1.1 fit in row 11? It's bigger than 10%. So this area over here, we don't know what it is, but it's bigger than 10%. So it could be 12% or 14% or 15%. Okay. Well, if this area is large, what do? We accept the null, and we find out that the source of all knowledge is totally plausible. It could totally be correct. Okay. Now, does this mean that Wikipedia is right? No. What does it mean? That it could be right, and more specifically, it means we don't think they're wrong, or we can't show that it's wrong. Okay? We'll never know the true average height, But we don't have enough information to tell Wikipedia to take a hike. Okay? So somebody asks us to do this study and they say, prove that Wikipedia is wrong. Well, we tried. We can't prove they're wrong. We can't prove they're right either. But we don't have enough information to say Wikipedia is wrong. Okay? And when we reject the null in other problems, we don't even make a claim on what we think the real percentage or average is. We just say it's not that. It's probably something smaller than that or something bigger than that. Okay, last one. A four-sided dice is rolled 6 times and the number 2 comes up 3 times. Is the dice fair? Now, is a sample of size 6 ever a good idea? Well, theoretically, no. But what if that's all you have? Right? You know, you're doing this experiment with a rat. You have one rat. You run the experiment 6 times and the rat dies. What do? You do a t-test. You were hoping to run the experiment 400 times, but you killed the rat. So, when I was at BYU, we did a study where the math ed department taught a calculus class that was structured far different than a traditional calculus class. Okay? And they wanted to know, do the kids in this class perform as well as kids in the other class? So we sat down with the statistician and they said, well, we have 30 people in the class, so we have a sample of 30. And the statistician said, no, you have one class, which means you have a sample of 1. That's a problem, right? Because you're comparing the class to other classes. So sometimes you only have a few number of draws because getting more than that is problematic or impossible. So that's why the t-test was created, right? So the guy who was brewing beer in Ireland, right? He might have only had 5 vats to brew in. So that was a sample of 5. So when you're rolling dice, 6 is probably not a very good idea. But if that's all you have, then just run a t-test. So what do we expect to be in the middle? We expect 4 to show up 1 in 6 times. As a percentage, that's 16.6 repeating. Oh, is it 4-sided dice? Oh, sorry. 0.25. It's a 4-sided dice. And when we do our sample, we end up with 50%. Now, if I just told you I'm rolling dice and I'm going to count the number of 2s, I'm supposed to get 25%, but when I did my experiment, I got 50%. Oh, 3 times? Boy. Holy cow. Thank you. Oh, no, it's 50%. 3 out of 6. Yeah. So if I told you that my sample had 50% 2s, you would probably tell me that the dice is unfair. But before you tell me that, you should ask, how many times did you roll? Right? Because if I rolled 1,000 times and half of them were 2s, something's wrong. And then I tell you, oh, I only rolled 6 times. And after you make fun of me for being dumb, then you say, okay, we'll run a t-test. So the null says fair, or the number of 2s is equal to 25%. The alternative says unfair, or the number of 2s is greater than 25%. Okay, so I need to create an SD. What should I use to create my SD? You use that whenever you can. When you can't, then you use the SD from the sample. So the square root of 0.25 times 0.75 gives me 4 or 0.433. What do I do to that? I need to create an SD plus. So I multiply it by the square root of 6 divided by 5. And that's going to bump the SD a little bit higher. So it turns it into 0.474. So that is my SD plus. What do I do to the SD plus? Turn it into an SEP. So I divide that by the square root of 6. Do I need to turn that into a percentage? Yes. So my SEP is 19.4. Okay. Now I need to calculate a t value. So I find the difference, which is 25, and I divide that by my answer times 100. That's supposed to be answer, not minus or negative. Wow, I'm really not doing this. I'm turning it to a percentage. And I get a t-score of 1.29. Which row on the t-table do I look at? 5. So I go to 5, and then I look for 1.29. Where is 1.29 in row 5? It's bigger than 10%. So this area right here, P is greater than 10%. Which means I accept the null, which means the coin's fair. Now, does it really mean the coin's fair? No, it means we can't say it's unfair. It still might be unfair, but from the information we gathered, we cannot say it's unfair, which is kind of nice. You don't have to own anything in statistics. Yeah. All right, that help?